Hey class, this is part 3 of chapter 15 problems. This is 42b. And here we have our equation. There we go. Here we have our equation and we know what the Kp is. Now Kp, I chose this problem basically because I want to make sure that you guys got a chance to do a problem with Kp in it. So let me show you what Kp looks like. Our Kp expression for this is going to look like we're going to do the same thing we did before, products over reactants, but in this time not using the brackets to mean molarity. So this problem is different from 42a because we're not using the brackets and we're not using the molarity equation of moles over volume. So we're going to use a different equation. I'm going to show you what that is in 1 second. But let's write out the K expression for this, the equilibrium constant expression, which looks like this. That's SO3 squared. Let me see if I can bring that down just a little bit. Move this down and move that down. There we go. And all of that is going to be over the pressure squared of SO2 and the pressure of O2. It's going to look like that. It looks like my board's starting to go a little wonky. All of that is going to be equal to 3.0 times 10 to the negative fourth, or to the positive fourth. Excellent. Okay. Now, notice last time we used the molarity equals moles per volume. Okay. And then I'm going to erase that because we're not using that this time. We don't have an equation like that that deals with pressure, but we do have a different equation that is very well known that I'm hoping that you've heard me use before, and that's the ideal gas law. Pressure times volume equals number of moles times the gas law constant times temperature. So let's see what we do have. We have volume here. Volume is 2 liters. That's in the problem. We have temperature. Temperature is 700 Kelvin. We know what R is. We're going to use 0.0821. That is liters, atmospheres per mole Kelvin. Okay? And these are dots. The dots mean multiplication in between. So MOL dot K, but because my board's screwing up a little bit, that looks a little different. So here's what we're going to do. The first thing we can do is notice that we're given, for SO3, we're given the number of grams here, and for O2, we're given the number of grams. I'm going to change both those into moles, and then I'm going to use my P equals nRT over V. I'm going to solve for pressure, and then we can plug it into this equation, the equation that we have for Kp. Okay, so once this is going to look like a lot of work. It's some of the stuff we've done before, and I'm going to show you how to use the PV equals nRT equation to solve for what you need. So that's our game plan. This is going to take a little bit, and it's going to look like a lot of work. So follow along, please. I'll try and go a little bit slower, but we do have a lot of work to do. So let's do 1.57. That's a 7. This is killing me here. Yeah, okay, now it's not even lined up right. Grams, and that is of SO3, and put that all over 1. And we do our typical mole conversion, which means moles of SO3. Now, when I do moles of SO3, that means the S is 32.1 plus 3 oxygens, and each oxygen is 16, so 3 times 16 is 48. Okay, so 3 times 16 is 48 plus 32.1, and that equals 80.1 grams per mole of sulfur trioxide. Okay, so whatever I get for this, the 1.57 times, divided by 80.1 gives me 0.0196 moles, okay, of SO3. Okay, now I'm going to do the same thing again. I'm going to do it for oxygen though. So I'm going to move down a little bit. We're going to be using a lot of this screen to do our calculations. So the next part says I got 0.125 grams of O2. That's in the problem right above, and I'm going to change that also to moles. So now I got moles of O2. Notice it's O2, which means not 16 grams per mole, but 32 grams per mole. Okay, and when I take the 0.125 grams of oxygen divided by 32, I get something that looks like this. And that's moles of O2. Okay, good. So now we got the moles part. So actually, if we take a look at our equation, the letter N is the number of moles of the gas that we're talking about. So now we have the N for both SO3 and we have the N for O2. So here's what I'm going to do. I'm going to simply use, now I'm going to scroll down a little bit longer, and then I'm going to plug in all the stuff we know for P equals nRT over V. Okay, I know that sounds kind of strange, but see if you can follow along. So the pressure of SO3 is going to look like this. It's going to be nRT divided by V. Okay, when I plug everything in there, I use the number I just got, which is the 0.0196 like this, times R, which is 0.0821, times 700 Kelvin, like that. And then I'm going to divide all of that by 2. When I divide all of that by 2 liters, what I get then is the pressure of SO3 is equal to 0.563, and that is in atmospheres. Okay, that's in atmospheres, and that's a pressure unit. So the pressure you're feeling right now is 1 atmosphere. So this pressure of SO3 is a little bit more than half of the pressure that you feel right now. I'm going to do exactly the same thing. I need a little bit more room. I'm going to do exactly the same thing for oxygen, and it's going to look like this: pressure of O2. Okay, again, it's nRT divided by V, so I plug those in there, and I got my 0.0039 for the moles, same R value, and same temperature, like that. And then I divide it by the same there, like that. So the pressure of O2 then is equal to 0.1121, and that's my amount of atmospheres. I could round that off 3 places, but that's fine. So now here's the big deal. Once I got the pressure for SO3 and the pressure for O2, I'm going to scroll back up to the top so we can take a look at as to how we're going to use that information. So now all I'm going to do is I'm going to solve. We're actually looking for, I'm going to change the red so you can see this. We're actually looking for this term right here. The pressure of SO2, and that pressure is squared. So it's going to be the pressure squared of SO2 equals, and all I'm going to do is switch these two. Algebraically it works. So the Kp comes in underneath the equation on the denominator, and the pressure of SO2 squared is up top. So let's do that down below. Now I'm doing everything in red to make it look a little bit different. You can see the difference for this equation. So here's what I just said. The pressure of SO2 squared equals, and then it's going to be the pressure squared of SO3 over the Kp times, and then the pressure of O2, like that. Okay? All I have to do then is plug in all of this stuff, which is 0.563, that's atmospheres, and that is squared. And then this one is 3.0 times 10 to the 4th. Okay, that is not squared, and that is times 0.1121, and that is not squared. Okay, whatever this equals here, because of this square root right here, I'm going to take the square root of whatever that number is. So the first number here, let's find out. I didn't actually do this calculation without I didn't write this number down. So let's do it quickly and write the number down. So that is 0.563. I'm going to turn it to the side and hit squared, and then divided by 30,000, and then divided again by 0.1121, and that equals, okay, so this equals 9.43 times 10 to the negative 5th. Okay, let me put this down here and write that down. So this is equal to 9.43 times 10 to the negative 5th. If you're following along, which I hope you are, then I would just put this number down here, 43 times 10 to the negative 5th. And when I take the square root of that number there, then I should get a number that looks like 0.00971. Okay? 0.00971. And that is in atmospheres. Excellent. Nice work. That's it. Please, ask questions, because I know that's a doozy. Talk to you later.